it is so great to be in Dallas, and I have driven by this church many times and never actually been inside it. It's just extraordinary, and I know I speak for everyone at Discovery Institute. Thank you to this church and to the staff for letting us have this event here. This crowd, honestly, this is on a Saturday morning to talk about science, essentially, and apologetics. This is remarkable. And so the Discovery Institute staff in Seattle were somewhat skeptical. They thought, well, maybe 80 or 100 people, right, could get to this. The demographics are quite different in Dallas than they are in Seattle. And us Texans actually knew that. So it's great to be with you. You heard last night and you heard this morning from Steve. Well, I want you to think about what we're doing today and last night as sort of giving you little loci, little locations within the natural world in which the evidence for purpose and design speak really loudly. The idea isn't that, just that God every so often is sometimes involved and otherwise leaves the universe to go on its own, but that rather God has created the universe, he sustains it, and then he leaves his fingerprints on the evidence. As Eric Metaxas said, it's like every cell in our bodies has made in Yahweh signed on it. And because of that, there are places in which we gain new understanding about some aspect of the created order in which the evidence for purpose and design, it just screams really loudly and really obviously for those with ears to hear and eyes to see. And so that's what we're doing. We're just sort of pointing at a few of those things. And so Steve talked this morning about the evidence for a beginning. And there's never been a better time in the history of the human race, in some ways, to be a theist and to doubt materialism. Because until the early into the mid-20th century, you could reasonably think that the universe was eternal. You could just sort of take its existence for granted. So if somebody said, where did the universe come from? You could just say, well, I don't think it came from anywhere. I just think it's the given thing. It's the reality from which everything else comes. No one expected that the universe itself would give observational evidence that it hasn't always existed. Think about that for a minute. If you believe in God and you believe that in the beginning God created the heavens and the earth, you believed that there was a beginning. Right, but people didn't really imagine that actually looking through telescopes and developing high-level theories in physics to explain the movements of the universe would entail, and then people would discover that the universe, in fact, had to have a beginning. Every time you hear the age of the universe cited, you should be amazed and wonder. The universe has an age. As Christians, we get in arguments about what the age is, and we miss the fact that if it has an age, it had a beginning. And if it had a beginning, it can't always have existed. So matter, the material universe, just can't be the fundamental reality. Unless you're willing to say, as Stephen Hawking did, as Steve Meyer quoted here, that the universe brings itself into existence. So a thing that doesn't exist. So if it doesn't exist, it can't have causal powers, right? It can't have any properties because it doesn't exist. Nevertheless, brought itself into existence with the law of gravity, which is a property of the universe once it exists. Right, this is what you call the reduction to the absurd of materialism. This is where we've gotten them now at the beginning of the 21st century. If you're a materialist, is you have to say the universe which didn't exist created itself. All right, and so my view as a Christian is, look, if you want that proposal, take that. But that's not an especially sort of persuasive conclusion. So we've got a universe with a beginning. And then as you heard a hint of at the end of Steve's talk, and as he talked about a bit last night and Eric talked about this morning, the universe, as we observe it at the universal scale, so the properties that the universe has as a whole, the things that are called the fundamental constants of nature. The constant just means it's constant. It's the same here. It's the same in the Andromeda galaxy. Everywhere we can look, the gravitational force constant has the same value. The electromagnetic force constant, it has the same value. So these are things that are true everywhere in the universe, are exquisitely fine-tuned in this sense, that if they were slightly different, let's say the gravitational force was slightly stronger or slightly weaker, you wouldn't just get a different universe. You wouldn't get a universe at all. You either get a universe that would have started its expansion and then would just dissipate into a kind of hydrogenated soup that doesn't do anything, or you'd get an initial expansion and the universe would collapse immediately back upon itself. That's the idea. So these constants, it's like they're resting on a razor's edge so that if they were slightly different, you wouldn't get a universe that was compatible with any sort of life. That's the so-called fine-tuning problem. And it applies, as I said, to the constants. It applies to the laws themselves, which are these sort of, you see them as equations with constants inside them. And then it applies to the so-called initial conditions of the universe, which is just the way that things would need to be set up at the beginning in order to have the orderly universe that you have, that we see before us. Think about it as this kind of vast billiard ball table with 10,000 balls, right? And you're going to try to sink them all at once. You're going to need the initial setup of the balls to be really special, right, to pull that off. That's the initial conditions. But the ways the balls interact, how hard they can hit, and those things, those are the constants. That's the idea of the fine-tuning of the universe. And I think it's one of those two pieces of evidence by themselves. I would argue this isn't a deductive proof of the existence of God, but it's something you would absolutely expect if you believed in the existence of God. And as Steve said, these have profound theological implications. These are much more likely and make much more sense if there's a transcendent God than if the material story is true. So with that as backdrop, I want to talk a little bit about all the evidence essentially from the origin of the universe to the origin of the first life. So I'm not going to talk about what you need to get life itself. Steve's going to actually, I think, talk about that after lunch, and Jim Tour is going to talk about that. What I want to talk about is what do you need to get just to get a planet that can host life, right? You need certain ingredients just to get an environment in which life is possible. So philosophers would say this is a question of what are the necessary conditions planetarily for life. But I'm not going to talk about the sufficient conditions. So all that space before you get to the origin of life. And this is the subject usually of astrobiology and of astronomy. And then sometimes cosmology. Cosmology, as Steve said, that's just the study of the cosmos as a whole. And that wasn't even a science in the early 20th century. In fact, many scientists said science doesn't even ask the question where the universe came from. It just presupposes its existence. But once we realized the universe had a beginning and could study the universe as a whole, a new science called cosmology developed. And so now it's a respectable field. But a lot of people don't know what that is. In fact, when I was writing The Privileged Planet, and Guillermo and I wrote this while doing other things, and so a bunch of my part of the book was actually written on airplanes. And so I try to give off the vibe that I don't really want to talk when I'm riding on airplanes. I do this. But some people don't kind of read the vibes exactly right. And I remember I was working on this book, and there was a woman sitting next to me, and she was with another group of women that were in the rows around me, and they were all seemed very excited. I thought, okay, they're all friends. Thought I'm going to have a hard time here writing probably. And so I'm trying to write, and I could see her looking at me and looking at my screen. And within a few seconds, she said, "Oh, what are you doing?" "Oh, I'm writing a book. It's a science book," which usually that's a conversation killer right there, But that didn't do it. And she goes, "Oh, well, what's it like?" And I thought, now I'm going to really kill it. "Oh, it's a book about cosmology." And you know what she said? She said, "Cosmology? I can't believe it. My friends and I, we just came from a 3-day conference on cosmology. This is our stuff. We live and breathe this stuff. Tell us about it." And so we had a little bit of a conversation. So they had gone to a Mary Kay convention. This was yeah. So I didn't get anything written on that flight. So this was, cosmetology is not cosmology. Cosmology is the study of the universe as a whole. And so really, this is why it's so important, because cosmology, as you can imagine, is one of the fields that touches closely onto philosophy and theology, because you're talking about the whole show. And so cosmologists tend to talk about these things. And then astronomers, in some ways, by derivation, tend to do that as well. Eric Metaxas mentioned this morning Carl Sagan, who's now the deceased Carl Sagan, but he was in the 70s and the 80s the leading public intellectual making the case for materialism. That's now passed to Neil deGrasse Tyson and then Bill Nye, the science guy. So, how the mighty have fallen. We've got Bill Nye now instead of Carl Sagan, the Cornell professor. But Sagan was a deeply committed materialist who also kind of wanted to have a type of spirituality. And in a famous documentary series on PBS aired around 1980 called Cosmos, he comes on at one point in this, and then there's also a book based upon it. And he had a very nice sonorous voice, and he says, "The cosmos is all that is, or ever was, or ever will be." Now, any of you that go to a church that sings the Gloria Patri know what that he's echoing there. As it was in the beginning, is now, and ever shall be. It's a reference to the eternal God who has always existed. And Sagan is attributing to the Creator, to the created things that ought to be attributed only to the Creator. But he knew exactly what he was doing. He's saying the cosmos, the physical universe, it's the fundamental reality. Now, this was 1980. Remember what Eric Metaxas told you a little bit ago and what Steve was telling you about the 1920s? Carl Sagan knew in 1980 that the scientific evidence itself suggested the universe had not always existed. So why was he saying this in 1980? He was saying it because of the metaphysical pressure of materialism. Whatever your worldview is, you need a fundamental reality, and that fundamental reality needs always to have existed. It needs to exist necessarily. And so you're going to hold on to that commitment as long as you absolutely can. And so Sagan was still willing to offer this doctrinal statement on PBS, and PBS was perfectly happy and willing to air it without any sort of disclaimers before or after. Well, sort of an associate idea of this materialism is something called the Copernican principle. And the Copernican principle just basically says the material universe is all that is, and all that ever was, and all that ever will be, is here as the result of entirely blind and impersonal processes. And as it turns out, whatever happened here on the earth must have happened countless times elsewhere, because there's nothing special about us or about our location in the universe, about human beings or about the earth or anything like that. And so this is just kind of something that follows if you're a materialist. And Sagan wrote a book sometime later called Pale Blue Dot, in which he offers this idea. And in the book, he reflects on an event that he was responsible for. The Voyager satellites, or the satellites that the US sent out to the outer reaches of the solar system in the late 1970s. And when they got out past the orbit of Pluto, Sagan was actually able to go to the NASA administrator and ask them, would you turn one of the cameras around to the inner part of the solar system and take a picture of the Earth from this, it's about 4 billion miles away. And this wasn't part of the mission, but he had the kind of credentialing to be able to do this. So they did, and they took a picture, and he said he was going to use it to help us realize how fragile our existence was, hoping that it would bring human beings together to see this fragile little planet. But when the pictures came out from NASA, there's an error, kind of a glitch in the photograph in which you've got a beam of sunlight. And so what you see is a tiny little pale blue dot. And then this little reflection of sunlight kind of cutting across it, which is just sort of the optics of the picture. And so then when he wrote the book, this is what he actually said about it. So this is the lesson that he ended up drawing from this photograph. So because of the reflection of sunlight, the Earth seems to be sitting in a beam of light, as if there was some special significance to this small world. But it's just an accident of geometry and optics, our posturings, our imagined self-importance, the delusion that we hold some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. Don't you know, this guy was a lot of fun at parties with this stuff. It's like, but notice this is a different lesson. This isn't let's be kind to each other and to our fellow human beings because we just have one planet. It's just a speck of dust in the middle of some obscure part of the universe that has sort of no help coming from anywhere, right? And so the question is, this is clearly a metaphysical and a philosophical claim. I think a bad one. It's not that philosophical claims are bad, but this is bad leftover materialist philosophy that looks like it might be based on the evidence. But is it true? If we actually look at the evidence itself, is it really true that we and the Earth are an insignificant speck in the universe? Or is the truth otherwise? Well, it turns out pretty much everything we learn and we know, we find there's actually a heck of a lot very special about the Earth itself. Just think how things have changed. In the 1930s, Orson Welles had a radio program called War of the Worlds that was fictional, but it was about these Martians coming from Mars and invading the Earth. And people that came in late to listen to the War of the Worlds maybe come in after the beginning. Many Americans actually thought it was a radio program, a news program, and panicked about these Martians invading. The reason is because a lot of people thought there might be intelligent aliens on Mars. What do we do now? We spend hundreds of millions of dollars to send probes to Mars to look for evidence of liquid water in the distant past on Mars. That's how precise we already realize that you need things to be in order for life to even be possible. Mars is the most Earth-like planet other than the Earth that we've ever discovered. The most Earth-like and it's lifeless. So that tells you that it sounds like you might need to get a whole lot of things right. And this isn't just the result of a lack of imagination on the part of astronomers. In fact, from chemistry itself, we now know that the planetary requirements for life are going to be very, very narrow. There was a time when the periodic table of the elements, first of all, it hadn't been constructed. And then there was a time after the sort of general layout was constructed that there were some openings, some elements that needed to exist but that hadn't yet been discovered, like helium. But now the periodic table of the elements is filled in. Everywhere we look, in every galaxy, anywhere in the universe that we can see, it's the same chemical elements obeying the same basic laws that will involve the same sorts of reactions. And so we know a heck of a lot based simply on the needs of life on a chemical basis for what you're going to need in any kind of planetary environment in this universe where the same laws of chemistry hold. And the result of that, I'm just kind of eliding over a lot of details here. But this is the gist of it. If you're going to have a complex life anywhere in the universe, you're going to want two things. You're going to want that life to be based on carbon chemistry, and you're going to want it to exist in the context of liquid water. So a bunch of reasons for this, but the simplest way to think about it is that there's no other substance, there's no other element in the universe like carbon that's really good both at building three-dimensional complex information-rich molecules, at coding linear information in molecules, which is what you're going to need for chemically based life, right? Both to build molecules and bodies and cells and things like that, but also to encode information that can be passed on, right? So that's just a basic need for any kind of life. And so it's going to need to be able to be encoded and build up complex molecules, but not be so stable that it can't undergo chemical reactions. So it's going to need to be what is called metastable. So just at the right sweet spot where it's stable enough that you can build a lot of complex stuff, but not so stable that you can't have chemical reactions, all right? And so that's the one need you're going to have. The other thing is you're going to need a matrix where these chemical reactions can take place. Well, it just so happens that carbon chemistry is most reactive over the same narrow range of temperatures over which water is liquid. All right, so think of the range of possible temperatures in the universe from, intergalactic space near absolute zero to the surface of stars. There's only, 100 degrees Celsius where water is liquid, and there's one element that's most reactive over that same range. So what that means is that liquid water and carbon chemistry are fit like a hand in glove for life. And so this is why we don't waste our time looking for life on the sun. We send probes to Mars because we know you gotta have water. And so it doesn't mean that if you have water, it's just add water and you get life. It's that you need at least water in order to have life. Now, why does this matter? It matters because what this means is we can already rule out, even in a universe that is exquisitely fine-tuned for life, a very big universe in which a lot of stuff can take place, most of the places are not going to be compatible with life. So already by itself, we know that Earth is going to be a very unusual place. And everything we've learned in astrobiology, and my co-author Guillermo Gonzalez is the expert in this, I'm just summarizing it, have led to the conclusion as we learn more and more that the list of ingredients you need to build a so-called habitable planet just gets longer and longer and longer and more complex. Again, this is a kind of cartoonishly simple idea here, but what kind of things do you need? As I mentioned, you need liquid water. And you don't just need water sort of floating in interstellar space. You need the right kind of planet. You need a surface for that water and a surface for life. And not just any old kind of planet. You need a so-called terrestrial planet, which that actually means Earth-like. But think of it as a rocky planet with a surface. The planet needs to be the right size. Too small, it won't be able to hold things and like an atmosphere on its surface. Too large, and you end up with something like Jupiter or Saturn with way too much hydrogen and things like that. So it needs to be the right size. It needs to be made up of the right kinds of things, something like a liquid iron core like we have that creates a magnetic field around the surface of the planet which protects life and the atmosphere. Turns out you need a large stabilizing moon like ours. The moon, it turns out, if we were to blow up the moon, over several thousand years, the Earth would start wobbling erratically on its axis. It'd also mess up the tides. So we didn't know this, but if the moon were not in our sky, we probably would not be here because Earth would not probably be compatible, at least with large animal life. You need plate tectonics that keeps the kind of long-range cycles of carbon up on the surface and keeps the stuff that life needs up near the surface. You need the right kind of atmosphere, probably a nitrogen and oxygen-rich atmosphere. Again, I'm just gliding over this, but when you've got carbon chemistry, you get just some kinds of atmospheres that work and some that won't. You need the right kind of planetary neighbors, believe it or not. Astrologers always believed that the planets played some role in our existence. I think they're wrong in general, but they were right, at least in this sense, that if we didn't have large outer-lying planets in our solar system like Jupiter and Saturn, the inner part of the solar system would be visited by far more comets from the outer part of the solar system. But because of these giant planets in the outer solar system, they think of them as sentinels that protect our neighborhood of the solar system from too many bombarding comets. Comets are sort of like your crazy aunt. You don't want them visiting so often, just every so often. And unlike your aunt, their problem is they can vaporize life on a planet. So it's like, please don't visit very often. And so, actually something like an arrangement of the solar system we have is actually really important for the habitability of Earth. Even though those other planets aren't habitable, they play a role in making the Earth habitable. Then you need to be around the right kind of star, the right size, the right age. It needs to almost certainly be a single star. Most stars in our galaxy are either together, either triplet or binary stars. You need to be in the right galaxy, the right kind of galaxy. You need to be in the right place in the galaxy, the right galactic location. And you need to be at the right time in the history of the cosmos. Now, I'm not going to assume that all of you just remember this from your 7th grade physics class. And so I'm just going to remind you. So we're on a planet in a solar system around a single star. We're the third planet from the sun. Depending upon your partisan views on Pluto, there are either 8 or 9 planets. All right, and Pluto, I'm a pro-Pluto partisan. So 9. Guillermo and I disagree on this. Okay, our solar system, so solar system means a system around this star that we call the sun, is just one of many stars in the Milky Way galaxy. And I'll show you a picture of that in a minute. And there may be between 100 and 300 billion stars just in the Milky Way. But the Milky Way itself is just one of between 100 and 300 billion galaxies in the observable universe. So exponentially, that would be 3 times 10 to the 22 total stars sort of available, right? So that's a very, very big universe. In a universe that is itself fine-tuned, very much precisely fine-tuned for complex life. So when you hear that picture and you say, gosh, you got to get all that stuff right, most people's intuitions, if they haven't had it bludgeoned out of them by a bad science or philosophy course, is that just bespeaks design. It's like Paley's watch resting on a heath. You need so many things to go right in a planetary environment that doesn't seem like that would happen by chance. Surely that by itself is design. Now, I think it is, but by itself, any slightly skeptical philosopher will tell you, by itself, just saying that the conditions for life in a habitable environment are rare doesn't get you a good design argument. And here's why. All right, so imagine I pull out a quarter from my pocket, which I would do if I carried cash, which I quit doing a few years ago. So pretend, right? And I say, okay, I'm going to flip this coin 10 times in a row, and I'm going to get 10 heads, and I tell you ahead of time. So I start flipping it, and everybody can see it, right? And I get 10 heads in a row, and I flipped it 10 times. Now, what are you going to immediately think? Was that a fair coin? He got 10 heads in a row, and he told us he was going to do that. Now, is it logically impossible? No. But the vastly more likely scenario is that I know a trick. I've got a magnetic thumb or a 2-headed coin or something like that. In other words, design, a setup, rather than chance is a much more likely explanation given that. Let's change the scenario. Let's say I'm going to get 10 heads in a row with this quarter, and nobody's leaving until I get 10 heads in a row, and you hear the doors lock. Right? And then I start flipping, and I'm fast, but I'm not that fast. Let's say I get 100 flips a minute or something like that, right? And so this goes on for a few weeks, and so some of you don't make it, unfortunately, because of your advanced age or whatever, but a few of you manage to survive, and you've been here for a long time, and we bring in water, and you've been here a few weeks, and I eventually get 10 heads in a row. Now, at that point, are you going to say, oh, chance could never have caused that? No. Because the opportunities for chance to operate were so wide, right? And so 10 heads in a row is bound to happen if you flip the coin 1,000,000 times. You're going to get that a lot. It's actually not that hard. I did this for my most recent book, and I thought I need to make sure it's fair, and so I flipped a nickel fairly 10 times in a row, and I got 7 heads in a row just by chance, right? So if you flip it 1,000,000 times, that's going to happen. This is the problem here, is that we know that Earth-like planets are going to be extremely rare in the universe relative to the number of places that you could be. But by itself, just something being highly improbable isn't a good design argument if there's also a whole lot of chance for room to operate. And so the skeptic could say, I grant you that Earth-like planets are probably really rare. They're not common like Sagan said. Nevertheless, it might just be, whatever you think about the beginning and cosmic fine-tuning, that this stuff just probably happened by a kind of cosmic lottery. And so that's why the argument that we actually make in The Privileged Planet isn't simply that. It's this. It's the idea that habitability, those things a planet needs for life, correlates with measurability. Those things that life needs also set up the best conditions for doing natural science. Right, so I want that to sink in because this is a different argument than the one you might have expected to hear. Here's how we put it in the book. By the way, this was Guillermo's idea for the title of the book, was Habitability Correlates with Measurability. And so if that had been the title, we wouldn't be here at this conference probably, because nobody would have heard of this book. So we came up with a better title later. But this is the basic idea. Here's how we put it in the book. It's the idea is the same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries. Or to put it differently, the very conditions that make Earth hospitable to intelligent life also make it well suited to viewing and analyzing the universe as a whole. So the idea is that those rare places where observers can exist also happen to be the very best places compared to the other options for doing observing. Now, this is one of these arguments called the cumulative case argument, where you have to give lots of examples, which I can't do just in a few minutes. So what I want to do is just kind of give you a couple of hints of what we're talking about, as examples of what we call this correlation between life and discovery. Perfect eclipses, solar eclipses, and galactic location. How many of you, summer before last, were in the path of totality for the solar eclipse? So some of you thought you saw it because you were at 85%. You didn't see nothing. Trust me, you got to be in the path of totality. It's absolutely unbelievable. So in 2024, you'll have another chance. So find your way to the path of totality and see a perfect solar eclipse or a total solar eclipse. Now, why is it so special? Why is it so unusual? Well, it's because of this very weird coincidence people have known about for hundreds of years, but had never really thought about. Now, what is an eclipse or a solar eclipse? To get a solar eclipse, to see it, you need 4 things to happen, really 5 things, all at once. You need a luminous body like the sun. You need an eclipsing body. In our case, it'd be the moon. You need an observer platform where observers can be. You need them to be the right distances apart. And then you need them all to line up in a straight line in space. And when these things happen, this set of coincidences, then if you're in the right place on the surface of that observer platform, you will see the moon, the eclipsing body, pass in front of the luminous body, in our case, the sun. And what people often don't really think about is that we don't just get total solar eclipses or eclipses of some sort. We get what you might call perfect eclipses, in which there is this near perfect match between the apparent size and shape of the moon and the sun on the sky. You can think about this. These are totally different bodies. You know, the moon is 400 times closer than the sun from the earth. It's also 400 times smaller. And so as a result of that, you get this eerie match between the sizes of these two things. And you get this weird match where right during totality, you can't do 20 seconds before totality, you can't look at it with the naked eye. The photosphere of the sun is so bright, you'll just totally mess up your eyes. As soon as it goes into totality, you can pull those dark glasses off and you look directly at it. You can see this outer part of the sun's atmosphere that you normally can't see. Well, my co-author, Guillermo Gonzalez, in the late 1990s, about the time we met, started thinking about this. He thought, this is weird. I wonder if you were on other planets in the solar system, if you could see eclipses like this, or what would the other eclipses be like in the other planets with moons in the solar system? And so he did a study, published an article in 1999. This is one of these things that's much more fun to report than I'm sure it was to actually gather the data on. But what this diagram, it'd take me about 10 minutes to fully fill it out for you. But what I want you to see is you've got a list of the planets on the left-hand side. And then left to right, you've got what's called the angular size ratio of a satellite to the sun. So basically, think of it as the size that something appears on your sky across a sort of angle, right? And if you have a ratio of 1.0, that means that they have exactly the same size on your sky. All right, and then there's a dotted vertical line going sort of down the middle of the diagram. Now those little horizontal dashes, what those are that basically where the different planets would be around if you're around Jupiter, for instance. Jupiter's got a lot of moons, so you can see Io and Ganymede and Europa and Callisto. They're too large, so their moons would be much larger than the sun. Saturn has a bunch. The long story short, run your eye down that middle line, the middle dashed line, and you'll notice two little lines that cross it. One for Earth and one for Saturn. Now, the one for Saturn is a moon called Prometheus, which is potato-shaped, and it whips around, but along one axis, it would be about the size of the sun for maybe a second, right? But notice that the moon crosses that line precisely. In other words, there's one place where you get this perfect match between the shape and the size of the moon and the sun in the solar system. It's the one place where there are observers to appreciate them. Now, by itself, that's just a weird thing to keep you up at night. That's not by itself a design argument, right? And so what does that have to do with anything? Well, now let me put two and two together here, because I remember I told you a minute ago there are a couple of really important conditions that you need for a habitable planet. One is, remember I told you need a large, well-placed moon. Another is you need to be around the right kind of star. And then you also need, I may not have even said, you need to be the right distance from your host star, in the so-called Goldilocks zone, where it's not too hot and not too cold for liquid water. And so when you get those two things, you get the large, well-placed moon. That's going to fix what your moon looks like in your sky and the size of it. And then you need to get the right distance from your host star. That's going to fix the appearance of the size of your sun in your sky. When you get two of these ingredients for building a habitable planet, it produces perfect solar eclipses, unlike all these other options. And as it happens, perfect solar eclipses play a very important role in the history of scientific discovery. Solar eclipses are like natural experiments set up to allow us to make scientific discoveries that would be very hard to do otherwise. I'll just give you one example very briefly. We talk a bunch about this in the book. If you feel like I just kind of brushed over this, we can punish you with a 444-page book that gives you absolutely all the details, and you can get it outside, all right? So I admit I'm glossing over this. But Steve Meyer mentioned relativity and the idea of general relativity, which is really Einstein's theory of gravity that he hoped would explain pretty much the sort of large movement of everything in the universe. And as he mentioned, according to general relativity, gravity is essentially the effect of mass on space-time. And so the more massive a body, the more that body curves space-time. And one of the implications of Einstein's theory is that a really massive body should be significant enough to curve space-time enough that the space-time around that body would actually change the trajectory of light passing nearby it. So he made a prediction that if you were to test the starlight from stars near the surface or the edge of the sun, right, sort of behind but passing near the edge of the sun, during a solar eclipse, and were able to map those stars at another time when the sun wasn't in the sky, that it would look like those stars had moved and gone someplace else, not because they'd actually moved, but because the light had curved as they passed around them. So here's the sort of basic idea, right, is that you map where the stars are normally in the sky when the sun's not up there, and then you map them again when the sun is in the sky. And because of the massiveness of the Earth and passing near it, the light passing near its edge, it would look like that star had moved. There's one problem with this experiment that you might guess. Try to do this experiment on like the midday, right? Are you going to see starlight right near the edge of the sun, right? This is one of these don't try it at home experiments. The only time this is going to work is when you get a perfect match of the moon blocking out the bright photosphere of the sun. So it turns out Einstein predicted this, and then in 1919, a team of astronomers led by Arthur Eddington tested this did the experiment, and confirmed Einstein's general theory of relativity. And this has been confirmed many times. In fact, when I saw the eclipse here summer before last, there were some NASA astronomers still testing this. But this was a hugely consequential discovery that led to the confirmation of one of the most important theories of the 20th century. And it was made possible because of perfect eclipse. So a set of conditions that makes the Earth habitable to life, that allows us to exist, then sets up conditions that make it better for a key type of scientific discovery, and we're able to make it here much better than we could have in other less habitable places. You get the basic idea? That's just one example. One more brief example. I mentioned that we are in a galaxy called the Milky Way galaxy. And so if you are ever to go up in the mountains somewhere, in fact, Jonathan Witt and I are childhood friends, who's also a fellow of Discovery here in Dallas, and he and I went to a camp for years in New Mexico as kids called Camp Blue Haven. It's over 7,000 feet above sea level. And so we were from Amarillo. And when I would always go to Camp Blue Haven at night, I would think there's always this weird misty cloud in the sky at night. I can't account for this. I thought it was so strange. And it wasn't until several years later when I was older that I found out, oh, actually, that's light from the Milky Way disk. What we're doing is we're looking edge on in toward the center of the Milky Way. And so we're looking through the kind of density of the gas and the dust and the stars in the Milky Way. And so if you get up in a really high elevation, you'll see that. That's why it's called the Milky Way. But the Milky Way is this flattened spiral disk of gas and dust and stars. And we're in it. We're one small member of that. And for a long time, astronomers just assumed, well, wherever you are in the galaxy, that will be fine. But in the last 20 or 30 years, astronomers have gotten much more impressed by the needs for the actual location. Even when you're in the right kind of galaxy, you need to be in the right galactic location, the so-called galactic habitable zone. Again, my co-author in 2001, before he was outed as an intelligent design proponent, I suppose, had co-authored a piece that was a cover story in Scientific American, not an ID publication, about the galactic habitable zone, and it's now a generally accepted idea. Is there going to be some places in the galaxy where you're just not going to want to look if you're trying to look for life? So here's the kind of basic story. Think of this as a bird's eye view of the Milky Way, if there were birds, out of the Milky Way. We're about midway between the center and the edge of the galaxy, between the Perseus and Sagittarius spiral arms. So about 27,000 light years from the center to the edge of the galaxy. Now that's actually the right place to be in. In fact, if we were in a radically different place, if we were in the inner part of the solar system or way on the outer part, we wouldn't be here. The reason is you get closer and closer to the center of the galaxy, there's probably a giant super black hole there. There are way too many stars. There's supernova going off. They're perturbing each other. Getting sucked up by a black hole, by the way, is lethal. If you didn't know that, you don't want this to happen. And so you don't want to be too close to the center of the galaxy. On the other hand, you want to be somewhat close to the center of the galaxy because that's where the heavy elements build up. And so you need things other than hydrogen and helium, one for a terrestrial planet and two for life. All right, and so if you get to the outer part of the solar system, it's astronomers call that metal poor, so not a lot of heavy elements. And so you want to be close enough to the center of the galaxy for there to be materials for planets and stuff like that, but not too close because of the kind of deadly stuff that's happening there in the neighborhood of the center part of the galaxy. So this is a technical diagram now that I've explained it to you in layman's terms. So you can see there's a kind of breakout here of our solar system, all right? And so then that's our sun, and then you notice the little kind of bluish green ring there. That's the circumstellar habitable zone, or the Goldilocks zone around our star. But then our star, our solar system itself, needs to be in a good neighborhood in the galaxy, about midway out between the center and the edge of the galaxy, between spiral arms, and rotating at about the same speed as the arms. Now, it's not surprising for me to tell you that's where we are, right? Because we wouldn't be here if that's not where we were. What's interesting is that it turns out that most of the places in the galaxy then aren't going to qualify. So even if we're looking for extraterrestrial life elsewhere, we're going to want to look nearby in the galactic habitable zone. Now, that's interesting, but again, that's just evidence that habitable places are probably rare in the galaxy. But there's this whole separate question. What if you were to ask yourself, okay, where would you want to be if you could pick one place and you want to be able to learn about the recent past You want to be able to learn about the different types of stars. You want to be able to see the other planets in your solar system. You want to be able to see nearby and distant stars. You want to be able to figure out the galaxy that you're in and its shape. You want to be able to see distant galaxies, and so the foreground contaminants won't blind you to it. You want to be able to detect the cosmic background radiation that gives evidence for a beginning. And you can only pick one place. Where do you think it is? It's in the galactic habitable zone, the one place where we are. In other words, the one place, little neighborhood in the galaxy where life can exist is also the best place for doing astronomy and several other kinds of science. Now, I won't develop this into a kind of robust argument, but I want you to see, why does that matter? And you might think, I already get it. I see why it matters. But again, whenever we infer design, when the design inference is triggered, when we say that's a setup, that didn't just happen, there's usually two things that happen. One, it can be a highly improbable or complex event or structure, but also it conforms to an independently given pattern or a meaningful pattern, right, that we would associate with intelligent agencies. So if you imagine you're a mountain climber and somebody kidnaps you and they drop you on an island somewhere at the foot of a mountain and you don't know where it is, but you're a mountain climber. You know how to do that, so you just start climbing this mountain. And it's quite dry, and it gets drier and colder, and you get up to the top, and it turns out this massive mountain is on an island, and there's an ocean surrounding it. And much to your surprise and maybe dismay, when you get to the top, you see these massive telescopes. You're on Mauna Kea, on the big island of Hawaii. Now, you might be just a stupid mountain climber and a surfer or something like that, but you're not going to wonder why they put the telescopes on the top of the mountain, right? Because, of course, that's what you would do if you're going to, if you want to observe the heavens, you're going to put the telescope in a good place for observing. That's the pattern. You detect intelligence there. In the same way, if the universe is set up and fine-tuned not only for complex life, but to make discovery possible, so those rare places where life exists are also the best places for doing science, for discovering the universe around us, then that suggests that the universe is not just fine-tuned for life. And so this is our modest conclusion, is that the universe is fine-tuned so that environments habitable to observers will also provide the best overall conditions for observation and discovery. Or to put it differently, the universe is not just designed for life, it's designed for discovery.